Welcome back to another explainer. Okay, today we are stepping into the high-stakes, incredibly fast-paced world of structural concrete testing. When you look up at a towering skyscraper or drive across a massive bridge, you're looking at thousands of tons of concrete that had to be rigorously tested and verified before it ever hardened. But how exactly is that done? Today, we're tracing the precise journey of a single concrete sample according to standard practice A23.2-1C. So let's dive right into this. How do we actually know a skyscraper's concrete is safe before it cures? I mean, you can't just stare at a spinning cement mixer and magically guess its structural integrity, right? You've got to capture it, test it, and prove it. And doing that requires intersecting the concrete at exactly the right moment.
First things first, we've got to define what we're actually working with here. Plastic concrete. We're talking about fresh, completely unhardened concrete sampled right out of the truck agitator or mixer before it even thinks about setting. So the really crucial point here is that we are dealing with a highly volatile, super time-sensitive material. It's constantly changing, it's reacting, and it is starting to harden the absolute second it's mixed.
Here's our roadmap for tracking the journey of this sample today. We'll be looking at 1. The stakes of fresh concrete, 2. The perfect grab sample, 3. Volume requirements by size, 4. The 10-minute ticking clock, 5. Wet-sieving large aggregates, and finally, 6. Reporting and traceability. All right, let's get into it.
Section 1. The stakes of fresh concrete and why precision matters before the pour. Look, without a perfect initial sample, every single test you run in the lab later on is literally completely useless.
Clause 7.1.1 of the standard actually makes this super clear. It states, the procedures used in sampling include every precaution that will assist in obtaining samples that are truly representative of the nature and conditions of the concrete. I really want to emphasize that word, representative, because if your sample doesn't perfectly represent the whole batch inside that truck, man, you might approve a dangerously weak mix or reject a perfectly good one. This standard practice is basically our ultimate shield against structural failure. Move in right along to Section 2, the perfect grab sample. This is where we'll look at the bread analogy and the specific discharge window required to catch it.
So the standard defines a grab sample as the operation of securing at one point of the discharge the required volume of representative material in as short a period of time as possible. You're literally just passing a receptacle completely through the discharge stream. And here's a pretty wild detail. You absolutely cannot control the flow by messing with the gate opening. No way. The rate of discharge has to be regulated entirely by how fast the drum itself is revolving. So yeah, sheer speed and flawless technique are an absolute must here. But hey, you can't just grab a sample whenever you feel like it. You've got to wait until exactly 10% of the load has been discharged. Think of it kind of like slicing a freshly baked loaf of bread. You wouldn't judge the soft, uniform texture of the whole loaf just by eating that very first crusty end piece, would you? It's the exact same idea here. You toss out that first 10% of the pour because the very beginning of the batch just doesn't accurately represent the uniform middle. And naturally, this brings us to the other end of the spectrum. You absolutely have to finish your sampling before the 90% mark. You've got to stop grabbing before the very end of the batch so you can avoid that inconsistent heel or tail end of the truck's load. So your sweet spot for a truly representative grab sample, it is strictly between that 10% and 90% window. Nowhere else. Now there is one major exception to the single grab sample rule, and that's when you're sampling for uniformity. In this case, instead of one grab, you're actually getting 3 widely separated grab samples while the mixer is being completely emptied. But, and this is a massive but, you must keep these samples completely separate. They're for comparative purposes, to check if the mixer is actually doing its job evenly across the batch. So whatever you do, you never, ever combine them into one composite sample.
All right, Section 3, volume requirements by size. Let's talk about matching the sample to the test cylinder.
Because catching the concrete at the exact right moment is really only half the battle. You also need to make sure you grab enough of it. And the scale here is actually pretty fascinating. The volume you need depends entirely on the size of the molds you're casting for the lab. Like, if you're casting 3 100 by 200 millimeter cylinders, you need a minimum of 20 liters. Step up to 3 150 by 300 millimeter cylinders, boom, you need 30 liters. But if you're casting 3 of those large test beams, the 150 by 150 by 535 millimeter ones, the requirement jumps exponentially. You're going to need a minimum of 55 liters of plastic concrete. That is a lot of material to catch perfectly.
And what if your testing plan requires more than 3 specimens? Well, you have to add the volume of those extra specimens plus a 10% buffer just to be safe. There is a really cool efficiency built into the standard here, though. Concrete that's already been used for a slump test can actually be reused for other tests. The only catch is you have to thoroughly recombine and remix it with the entire sample first.
Okay, Section 4, the 10-minute ticking clock. This is where we look at the literal race against evaporation and segregation.
You really don't have all day to do this. The second your receptacle passes through that discharge stream at minute 0, a literal 10-minute countdown starts ticking. Within this exact 10-minute window, you've got to safely secure the sample, transport it to wherever the test specimens are being molded, and completely finish remixing the sample with a shovel. Why the rush? It ensures total uniformity before the material actually starts fundamentally changing its chemical and physical properties.
And keep in mind, during this 10-minute sprint, the technician isn't just battling the clock, they're battling the elements. The standard is extremely clear about this. You must protect the sample from the sun, the wind, and any other sources of rapid evaporation or contamination. If the concrete dries out or segregates, which basically means the heavy rocks sink to the bottom and the watery paste rises to the top, well, the sample is completely ruined. It no longer represents the actual concrete that's being poured into the structure.
Next up, Section 5, Wet-sieving large aggregates, dealing with chunks too big for the mold.
So what exactly happens when the aggregate rocks in your concrete are just physically too large to fit into your testing equipment? You've got to perform a procedure called wet-sieving. Basically, before you do your final remix, you pass the concrete over a designated ISO 23.2-1 sieve. You shake or vibrate it until all the undersized material passes through. But pay attention here, because this is a super critical baking recipe detail right out of the standard. If any wet mortar clings to those large discarded rocks, do not wipe it off. You literally just scrape the mortar from the sides of the sieving equipment itself straight into your batch can, and then you remix the remaining undersized batch with a shovel.
And here is the absolute aha moment from the source notes. Wet-sieving actually alters the properties of the sample. Think about it. The wet-sieved concrete fraction will actually have a naturally higher air content than the total concrete batch. Why? Because those giant rocks you just threw away, they contain absolutely zero air. On top of that, the apparent strength of wet-sieved concrete in smaller specimens usually tests higher than that of the total concrete. It's just a really fascinating quirk of the physics involved, and structural engineers actually have to account for this artificial bump in strength and air content when they're evaluating the final test results.
Which brings us to our final leg of the journey today. Section 6, Reporting and Traceability, the paperwork that guarantees structural safety.
Because, let's be honest, a perfectly caught, correctly sieved 10-minute grab sample is completely worthless if you don't have the paperwork to prove exactly where it came from. The documentation is incredibly rigorous. The report has to guarantee an absolutely unbroken chain of custody. We're talking the mix ID, the batch or bill number, the exact date on time of sampling, the project site ID, and the sampling location, like say if it was taken from a pump discharge instead of directly from the truck. And crucially, it needs the specific location in the structure being poured, the certified technician's name, the lab ID, a reviewer's signature, and notes on literally any deviations. This immense traceability is what links that tiny little 20-liter cylinder directly to the exact wall or floor it represents in a massive high-rise. Now, interestingly enough, Section 9 of the standard notes a pretty unique caveat. Precision and bias cannot be specified here. Why is that? Well, it's because this standard isn't actually about taking a measurement. It is strictly a physical sampling procedure. It's just a set of highly rigid instructions for the physical act of getting the material correctly in the first place, so that all those other later tests can actually do the measuring.
So, we've seen exactly how a single, perfectly executed sample acts as the ultimate guarantor of structural safety, racing against a strict 10-minute clock and battling the outdoor elements. I want to leave you with this thought. If the entire structural strength of a towering building relies so heavily on just a single grab sample, how strictly do you think those 10% and 90% rules are actually followed on your job site? Something to think about, right? Thanks for joining me on this explainer, and remember to keep asking the right questions about the built environment all around you. Catch you next time.